Welcome to my webinar. I'm Dominik Kunert. I'm a senior sales engineer for analytical application at HAMAMATSU Photonics. Today I want to talk about laser-induced breakdown spectroscopy, remote analyzing with the OOI principle. The presentation is structured as follows. After some general basics about laser-induced breakdown spectroscopy and an application example and further promising applications, we also look shortly on alternative techniques compared to LIBS, especially in metal environment. Then, the main topic, I introduce our newest developments and activities for detectors and lasers targeting LIBS, and finish this talk with a short summary. But first, a few introductory words about the company HAMAMATSU Photonics. Established in 1953, HAMAMATSU boasts over 5,000 employees worldwide and generates a net revenue worth $1.3 billion. Today, we can provide our customers more than 15,000 types of products as custom and standard version. We invest 9% of our revenue in extensive research and development, leading us to the contribution of 3 Nobel Prizes. With 7 manufacturing plants and several central research laboratories, we strive the real mysteries, accelerate diagnosis, and improve industrial yield for our end users. We are world leader in manufacturing optoelectronic components, modules, and systems, which we either integrate adding value to our OEM products or sell directly to our end customers. We are pushing our effort in light-powered innovation and develop technologies that capture, measure, and generate light through broad spectral range sensors from DUV to far infrared, high performance and stable light sources, customizable modules for detectors and emitters, high resolution spectral sensitive cameras. Furthermore, we are engaged to expand our laser portfolio step by step. And last but not least, we are combining photonic integrated systems for imaging technologies, detection, optimal image processing. Now back to LIBS. And what are the basics behind LIBS, or laser-induced breakdown spectroscopy? It's a kind of atomic emission spectroscopy and a technique for chemical analysis to determine either the presence or the mass fraction of an element present in a sample based on a measurement of the intensity of light emitted from a plasma. It is an established, straightforward, reliable, and versatile form of atomic emission spectroscopy that has a broad capability for rapid in situ elemental detection in any material, solid, liquid, or gas. This exemplary Bohr model shows random element in the ground state, and after the excited state, when an electron falls back in the ground state, a unique spectral fingerprint wavelengths will be emitted associated with discrete energy levels. In LIBS, a high-intensity pulsed laser beam is focused onto the surface of a sample, which creates a high-temperature plasma through the multi-stage breakdown process that occurs when the laser energy couples to the material, in other words, the laser-material interaction. Typically, a sub-milligram amount of a material is ablated, vaporized, and dissociated in a high-temperature plasma into the mixture of free electrons and weakly ionized materials, atomic ionic species. The plasma cools down rapidly, causing species recombination, de-excitation, and the release of energy as photons when electron returns to lower levels again. At its core, the analytical system basically consists only of the following components. First, a solid-state, short-pulse Q-switched laser operating at 1064 nanometer, used to create a microplasma on the target. Second, a set of optics to focus the laser light onto the target and to collect the light emitted as the plasma cools down again. And third, a coupled fiber optic and spectrometer detector system for acquisition of the plasma light emission and spectral resolution of the light spectrum. Fourth, and finally, a computer for system control and data processing. In general, the quality of the laser unit in combination with the detection unit are the key hardware components for a high accuracy measurement. And HAMAMATSU can provide both components in various integration levels. LIBS basically has the advantage of not requiring complicated pre-measurement processing of the target object in situ or on-site, regardless of the object state. As I mentioned before, this enables the high-speed, non-contact inspection required for inline inspection also allows analyzing a diverse range of substances such as plastics, metals, and glass. This means that LIBS provide as a promising technique for inline inspections at many kind of manufacturing sites. In an experiment setup at Tokushima University, LIBS was able to detect spectral properties for silicon, iron, carbon, and calcium, which are main constituent elements for fly ash and a kind of cold combustion product. This makes LIBS promising for real-time quality control by measuring such as steel slag composed of similar main properties that are byproducts of steel manufacturing. Also, it has an idea to measure the amount of carbon contained in fly ash and feed it back to control the combustion temperature of furnace. The diagram shows the wavelengths versus intensity, and stronger peaks of silicon and aluminum are already visible when we zoom in the wavelengths range from 247 nanometers to 255 nanometers. You can detect further atomic element peaks, so it's absolutely mandatory to have high-resolution detection unit with a high signal-to-noise ratio, which also complies industrial standards. To highlight some further applications like nuclear thermal power plants, where exemplary rapid identification and measurement of hydrogen and other light isotopes is done in nuclear materials, or steel or iron manufacturing process, which is done in high-temperature environment where analytical equipment cannot be installed nearby due to the extreme heat. This makes it difficult to obtain accurate results in analysis and inspection. But applying LIBS now ensures highly accurate properties analysis, even from remote locations. There are already plans to carry out all inspection processes in steel manufacturing, from selection of raw materials to the rolling process, in order to improve product quality. In semiconductor process field, to control various process-induced particles, which are generated during the semiconductor manufacturing process. And these are responsible for approximately high number of total defects observed in semiconductor products. In the recycling field, technology for accurately identifying large quantities of mixed waste materials is essential for achieving more efficient recycling. Using LIBS allows highly accurate screening of materials whose properties are difficult to identify visually, and so will help reuse resources more efficiently. And last but not least, LIBS could be also considered for in-vehicle lithium battery inspection. When we come back to metal analysis, there are still further alternative atomic emission spectroscopy techniques. For example, in X-Ray Fluorescence, a focused beam of X-rays is fired at the surface of the metal. This is high energy displaces electrons in the atoms. As soon as the electrons fall back in their ground state, they release a specific energy signature. In wavelengths dispersive XRF approach, a combination of scintillator, up-on photomultiplier, or maybe coupled semiconductor-based silicon photomultiplier can be used in detection unit. But the gold standard has been so far the arc spark-optical emission spectroscopy, where the metal surface of a probe is heated to thousands of degrees Celsius with electrical spark. The energy applied causes atoms in the metal to emit light, which will be analyzed, sample composition. Latest redesign activities in the optical system makes the system more compact. Ongoing developments in HAMAMATSU CMOS technology bring alternatives to CCD detectors or PMTs. But remote sensing is not really possible with OES. Generally, frankly speaking, there's no instrument that cover all needs, from the accurate trace element analysis to rapid sorting of alloys exemplary, and everything in between. So, can the latest developments of lasers and sensors bring LIBS to the next level, especially in limit of detection in remote inline analytics? Let's have a look. In this section, new image sensors will be introduced, and in a next high integration level, plus built-in accreting a spectrometer. The temporal process of one shot can be summarized as follows. The short pulsed laser excitation locally heats the sample on more than 10,000 degrees Celsius. In the first nanoseconds of plasma expansion, unspecific emissions are occurring after the laser excitation like in Earth's Bremsstrahlung, recombination radiation, or blackbody radiation. The Bremsstrahlung and the recombination radiation decay faster than the elemental specific emission. By time-delayed detection of this background signal or interference will be reduced and the signal-to-noise ratio will be increased. Typically, for a time-resolved approach, the delay time needs to be as short as possible, just like the integration. The latest developments of CCD detectors or charge-coupled device can provide extremely low image lag, so it is possible to activate the sensor's integration time close to the excitation to achieve highest as possible signal-to-noise ratio. Incentive image lag means unread signal charges in percentage due to the incomplete transferring of signals or charges from the photodiode, resistive gates, and the storage gate to the shift register. These unread charges or image lag are generated in the photosensitive area during the laser emission and the unspecific emission during alpha time. In this case, the all reset gate function is set high in the sensor, which also controls the electronic shutter function. In this setting, occurring signal charges are carried away from the storage gate into the all reset drain. This signal charge is then not accumulated. The smaller the alpha time, the higher the randomly occurring signal charges, which needs to move to all reset drain, and as conclusion, the probability is higher for remaining charges in the pixel. What means image lag? As soon as the all reset gate function and e-shutter function is set on low, an integration time starts. The newest detectors thus show improved characteristics for this time-resolved LIBS approach. For all of these three detectors, the pixel pitch is the same with 40 micrometers. The smaller the pixel height, the lower the image lag. When you are comparing the right detector with the other both, the number of pixels is the same, 2048 pixels. The maximum line rate is prescribed by the sensor's internal readout circuit. I explain a little bit more on the next slides. In addition, why the quantum efficiency and the dynamic range differ between the left and the middle sensor. We also have suitable boards for each of these sensors. Well, what are now the differences between the sensors in a more detailed view? The left one, the S15254, to perform charge transfer at high speed, a resistive gate structure is used in the photosensitive area. The back of the resistive gate is thinned, which enables the CCD to achieve high quantum efficiency over a wide spectral range, in the same manner as ordinary back-thin CCDs. The signal charge that is generated through photoelectric conversion at resistive gate is transferred to the storage gate by the potential slope that is formed by difference in the voltages that are applied across the resistive gate. The charges are directed upward and downward rapidly to the horizontal shift register. In contrary, the sensor S15351 is designed to receive the light from the front side, where the circuit pattern are formed. Due to this polysilicon electrodes, etc., the light entering is absorbed and largely reflected away. So quantum efficiency is typically lower compared to back-thin CCDs, where the light is entering from the backside. The photoactive area is thicker, which increases the full well capacity and the dynamic range. The interline transfer structure incorporates charge transfer channels called interline masks, which reduces the active area. These are immediately adjacent to each photodiode so that the accumulated charge can be rapidly shifted into the channels after image acquisition has been completed. Here again some further information about the measurement result of image lag between both sensors. The time alpha is the time between laser excitation and opening e-shutter. The blue sensor is the interline FT sensor, and the red sensor is the resistive gate back-thin S15254. Below, 1 microsecond time difference. So the resistive gate structure and back-thin design provides extremely low image lag values. Suitable driver boards available for these both sensors consist of a CCD driver circuit, an analog video signal processing circuit, integrated time generator, control circuit, and a power supply. By contacting USB 3.0 connected to a PC, it is possible to control the board, obtain data from the sensor. with a SMA connector is already mounted for external trigger input. This product already comes with application software. These driver boards will be also used in the next higher integration level, combined with some optics like grating and condensing mirror as a complete high resolution, 0.1 nanometer resolution typically, spectrometer for the UV range from 190 to 300 nanometer. In this version, the interface is realized with USB 3.1. We are currently working on the release. And now from the 1D to the 2D resolution. What does it mean? In some applications, it is needed to gather the spectral information with a 2D camera instead of a 1D spectrometer. In this concept design, we couple image intensifier with CMOS camera. The image intensifier, an image device capable of detecting and amplifying very low-level light. A photocathode that converts incoming light into the photoelectrodes, a microchannel plate, in other words MCP, that multiplies electrons by internal photoelectric effect, a phosphor screen that reconverts electrons into light arranged in close proximity in an evacuated case. This provides an image with no geometric distortion. Through this process, an input optical image is intensified about 10,000 times for one stage MCP and appears as the output image on the phosphor screen. The amplified image will be visualized with a high-sensitive digital CMOS camera with high-speed readout, making it ideal for imaging moving parts for LIBS. So what an ICMOS camera can achieve? In general, the image intensifier intensifies the incoming light. The combination of image intensifier and CMOS camera provides high signal-to-noise with fast gating time. The setup could permit lower laser power beam as conclusion reduced damage on the sample, and furthermore increase dynamic range by the internal amplification. Basically, the concept ICMOS consists of A, the intensifier unit, B, relay lens inverting an image and extends the optical tube, C, the Orca Spark CMOS camera, and D, as an add-on, a pulse generator. The CMOS camera has 2.3 megapixel effective numbers of pixels. The cell size is 5.83 micrometers times 5.83 micrometers, allows high resolution imaging. The readout noise only for the CMOS camera is 6.6 electrons root mean squared. As next, some facts about the intensifier unit. The image intensifier is considered to have gate time with 100 nanoseconds DC. Is this generally fast enough, or faster gating slots required? The maximum rotation frequency is indicated with 30 MHz. As cathode material, we use standard photocathode of multi-alkali material, as it is overspan a broad spectral range from 185 nanometers to 900 nanometers to detect a broad range of elements. As add-on, a pulse delay generator could be applied several channel pulse outputs for adjusting each timing of device in a measurement that uses a high-speed gated image intensifier or spectrometer or CCD or CMOS camera and xenon flash lamp or pulse laser as a source, so ideally fits for time-resolved LIBS setups. Last but not least, to create a plasma, we need a powerful pulse laser unit at 1064 nanometers. This graph compares laser pulse width versus pulse energy and clearly pointed out that you cannot use one single laser for each LIBS application. The requirements, depending on the applications, are complex. Simply put, high energy is needed for long distances, around 4 to 8 meters, but this is also influences the pulse width. For short distances, higher repetition and small pulse width are required, but the pulse energy is getting weaker. A happy medium is the energy in a high version with a short pulse. Generally, customized adjustments needs to be considered case by case. In the previous slide, this laser was already marked with a red dot as a high power and short pulse version for LIBS. High power means up to 8 microjoule per shot with a pulse width of approximately only 2 nanoseconds. It is possible to apply single shot abrade, but you can also apply up to 10 Hz shots. To run this unit, you only need to connect a power supply, a trigger generator, which makes it very easy to use. To bring all together at the end, image sensor, spectrometer, generally HAMAMATSU, can provide a variety of detector technologies for spectroscopy purposes, depending on the requirements of the application. Starting from the wafer process, the image sensors 1D or 2D will be produced in-house. We are controlling the complete production process and can apply custom requests. In higher integration levels, with view and driver boards or spectrometers, there is some room for modularization, other interfaces or so. When we are looking at ICMOS camera, in different HAMAMATSU divisions, all components inside the camera are in-house products. Our purpose is to provide high-gain products with high signal-to-noise for light use. In the interaction of the components, this ICMOS camera concept is also suitable for weak lasers, so to generate less damage on the material. So coming now to the laser modules. In general, this is in-house manufacturing consistently from laser diode to solid-state lasers. And there's some possibility for custom support. When we are looking on the 8 millijoule module, it's quite easy to operate. Single shot to several shots per second is feasible, and this 8 millijoule is quite powerful. Thank you for your attention, and if you have any questions or requests, please do not hesitate to contact me.